Okay, so we're starting chapter 5, which is looking at trigonometric identities. So basically what we want to look at today is you need to know what the basic trigonometric identities are after today. The reciprocal and quotient identities you already know. So those are going to be the first two slides and you'll recognize them right away. The Pythagorean theorem identities are pretty straightforward to get to. You'll probably just end up memorizing the three basic ones and then just know how to kind of morph them. But I'll show you where they come from. The cofunction and odd-even identities are kind of going to be the new ones. All right. For your second step, you're going to want to be able to use the identities, not just recognize them, but use them in order to simplify expressions with trigonometric values in them, and also solve trigonometric equations. All right, so let's get going. So your reciprocal identities. These are the ones that you guys already know. So you already know that the secant and the cosine are reciprocals of each other. You already know that the cosecant and the sine are reciprocals, and the cotangent and the tangent are reciprocals. That's stuff that we used in the last chapter. So I'll give you a second to write that down, and then we will move on. The quotient identities are also ones that you've already seen. So the one we've worked with the most has been sine over cosine is the tangent. And then obviously, since the cotangent is the reciprocal of the tangent, if you just flip that fraction to cosine over sine, that would give you the cotangent. So those should be the ones that look familiar. All right, so for example 1, we're going to start looking at the new identities that you haven't seen yet, the Pythagorean theorem identity. And we're going to kind of see where they come from so that if nothing else on a quiz or a test, if you forget them, you can discover them pretty easily. Although these are the three we're about to come up with right now that you'll probably just end up memorizing and working with those memorized identities. But here's where they come from. So this particular example says to pick any point on the unit circle. So I'm just going to pick something in quadrant 1 because it's easier. Or easiest, I guess. So notice that if I draw an axis real quick, and I pick any point on that, in that quadrant, let's say. So let's say I pick a quadrant or a point right there. Okay, it says to express the Pythagorean theorem of the reference triangle. So I need to draw the reference triangle of this. How do I do that?
From the origin and the x-axis.
Good. From the origin to the point, and then from the point, and very good, to the x-axis. And that's kind of the most important part, is that you do need to go to the x-axis, not the y-axis. All right? Something that some of you guys are messing up on the quest that I just kind of want to take this opportunity to point out is you need to put your reference angle in the right spot. Which angle do I put the reference angle in? Do I put it in this angle by the origin, or do I put it in this angle up here by the point? By the origin. On the test, some of you guys did a problem where you were putting the angle up here. That is incorrect. Okay, the reference angle should always be in here at the origin. All right? So when I am looking at this triangle, I have a point xy, and normally we would say that the distance along the x-axis on the triangle, that leg is x, this leg is y, and then my radius, since I'm assuming this is the unit circle that I've put one on, what am I assuming my radius is? I'm assuming that it's 1, right? But notice that I wanted to write the Pythagorean theorem, which Pythagorean theorem would normally say x squared plus y squared equals 1 squared, which would be 1, right? But I'm asking to do this in terms of the sine and the cosine. So what can I put in place of x in terms of sine and cosine? What is x? Cosine of. So this would be writing the cosine of theta squared plus, and then my y value is, what's my y value? The sine of theta squared. And that should equal 1. So all I've done is replace my x and my y with the equivalent representations in terms of sine and cosine. Does anyone have any questions on that? I'm looking over here at my x, that's going in as cosine, and my y is going in as sine, because on the unit circle, the x coordinate is the cosine, the y coordinate is the sine. That's what we've been using all last chapter. Okay, now typically we write things with sine first, so you'll see this same expression written as sine squared of theta. Notice that when we have an entire trig function squared, we put the square after or before the angle, right? So you'll notice that I took off the parentheses here, but I moved my squared inside. That's just so that I don't have parentheses everywhere, and it's distinguishing between having the trig function squared versus having the angle squared. Like if I left the square out here on the theta, that might look like the inside angle is squared and not the trig function. So that's all I'm doing there. That's a notation that you're going to want to get familiar with. And then we would say plus the cosine squared. So I've just switched the two terms is all. That's how you're going to see this particular identity. Is going to be this guy right here. Okay. So now
is there any reason why you switched the sine and the cosine?
So she just asked, is there any reason why I switched the sine and the cosine? There's no reason other than just that's the standard form that you'll see in textbooks. It just reads nicer, I guess. I don't really know. But it technically, if you write cosine squared plus sine squared, it's the same thing. Okay. Okay. So now we're being asked to write the same thing in terms of secant and tangent. Okay, I'm going to kind of show you how I'm going to work on this one, and then I want you to try and do the cosecant and cotangent on your own. But for the secant and the tangent, I am going to start with the Pythagorean theorem identity that I just came up with, because I know that this is true. And then I know that I can force a tangent out of that very first, a tangent squared, out of that very first term by dividing by the cosine squared of theta. That will get things in terms of tangent. But if I'm going to divide one thing, I need to divide all pieces by that same thing to keep the equation balanced, right? So when you go through this, you'll see that sine squared over cosine squared is equal to tangent squared of theta. Cosine squared over cosine squared is 1, and then 1 over the cosine squared is secant squared. Yep, we retain that squared of theta. So I've now written the Pythagorean theorem again in terms of two different trig functions. The thing to notice here is that in our very first, in our sine and cosine, we're adding the two trig functions to equal 1. Notice that down here, I'm adding the tangent onto 1 rather than the secant, and then that equals the secant. Do y'all see that? Kind of a different form here. This is going to have a similar form to this guy. So why don't you guys try and figure out what that cosecant and cotangent one looks like, and I'll put the solution up as well while you guys are working. All right, so that concludes the cosecant and the cotangent. This is what you should have gotten. You should have gotten divided by the sine squared this time, because then you end up with cosine over sine to force the cotangent, and then the cosecant follows from this. Notice that for these two identities, when you have the tangent and secant and cotangent and cosecant, the secant piece is by itself, right? And the tangent piece is plus 1. That's important to notice that that is not minus 1 on the tangent piece, right? Those little differences are going to show up, and you have to recognize when something actually is the identity or if it's close but not quite, okay? All right. So the next slide just shows these same identities. And that's exactly what we just found, but I'm going to show you that, or I want to point out that these, when we're working with them, might appear as is in this form, but there's two other ways that each of these might be written. And I want to see if you guys can tell me, I'm going to get you started. Tell me all the ways that each one could be written. So this guy right here could instead be written as cosine squared of theta. Hold on. Equals 1 minus the sine squared of theta. Right? How else could that be written? How else could you rearrange that same statement? Huh? Switch the sine and the cosine? Right, so you might have sine squared of theta equals 1 minus the cosine squared of theta. I also want to point out, you might have something along the lines of, what if instead of having 1 minus the cosine squared, I had the cosine squared of theta minus 1? Now what? Right, that's just changing the sign, negative sine squared of theta. So you have to be ready for that as well. You'll want to know when is it positive, when is it negative based on which order these are in. So you want to know, whether or not to tack on a negative. I usually just have this one memorized and I'll write it down on my paper and kind of visually look at how it's been rearranged to figure it out, right? But there's a bunch of different possibilities. I'm not going to go through all the rest because you can see how these will be rearranged as well, but you can just say kind of similar rearranging. Or I guess I would say be aware of similar rearranging. You don't have to erase, just kind of tack it on for the rest of these. Are there any questions on what I mean about watching that kind of stuff? That's actually the tricks to these problems that we're about to get into, is being able to see these Pythagorean theorem identities in different forms. That's why I'm kind of spending some time showing you that. Have these three memorized. I would just write them at the top of your sheet of paper and be ready to kind of look at them and see whether or not you have one of those in a different form. Okay? Any questions? All right. So I'm going to go through the rest of the identities. Cofunction identities basically say that if we have three different pairs of cofunctions. Okay, so the sine and the cosine are cofunction identities. All right, I've just rewritten them over here in a separate way. So sine and cosine again are cofunction identities. What it means to be a cofunction is that if you take pi minus 2, or that's the same thing as 90 degrees, and you subtract your given angle, it's equal to the cofunction of just the angle. So if you have something that looks like this in the angle with a pi over 2, you can simplify the expression by using the cofunction, and you can get rid of that pi over 2. Do you see what I'm saying? Okay, so cosine and sine are cofunctions, cotangent and tangent are cofunctions, and then the secant and cosecant are cofunctions. They all have that same property of taking, if you have a trig function of pi over 2 minus an angle, it equals whatever the cofunction is of just the angle. All right, so odd-even identities is just applying what you already know about odd and even functions. So this is what I want you to kind of focus on real quick. I'm going to write some stuff at the bottom. Remember that back in semester 1, I told you guys that an an even function, sorry about that. Let me get back up. All right. I told you that an even function is one in which if you plug in to the function a negative x, what do you expect to get out of it if it's an even function? What? Not just an x. You still want the function, but you want you just want the function back. So if you plug in a negative input, you get the same exact output. Nothing changes. Right? So if I were to plug in a 3 and a negative 3, I should get the exact same thing out. That's what even means. Okay? Odd means what? If you plug in a negative value, you get, or not a negative value, but the opposite of your input, you get a negative f of x out. Remember that graphically, an even function then means one in which it can reflect over the y-axis. Symmetric about the y-axis, right? And one that is odd is symmetric about the, what do we say? Right, symmetric about the origin, so it would look something like this. So you can remember these odd-even identities by kind of remembering the shape of a graph, right? So if you look at the sine function, remember the sine function about the origin is going to look like this. Is this an odd or is this an even function? Is it symmetric, perfectly symmetric about the y-axis? No, that is not perfectly symmetrical about the y-axis. Right? So this is actually an odd function, which is why they're saying if you plug in a negative theta, so that's where this comes in. If you plug in a negative theta, that's just like plugging in a negative x, you get the opposite of the function back. It's the same exact thing that we've been doing, right? So I want you guys just to visualize in your head, I'm not going to draw all the graphs out. The cosine function, is that symmetrical when you graph it? Is that symmetrical about the y-axis? That's why it's even. And when you plug in the negative input, you get just the regular old cosine out, not a negative. Okay? Think of the tangent graph. Is the tangent graph odd or even? It's odd, right. Remember the tangent graph, and just so you can kind of remember it. The tangent graph was the one where you had asymptotes straddling the origin, but you can see that that's not perfectly symmetrical about the origin. That's an odd graph, right? So this is odd, which is why when you plug in the negative input, you get a negative output back. And then the reciprocals just match up together. So sine is a reciprocal of cosecant, which is why the cosecant has the same exact values as the sine. And same thing with cosine and secant have the same values, so secant will be even, tangent and cotangent. So that's one way that you can kind of remember which functions are even, which ones are odd, and which ones have that negative input thing. All right. Okay, this next example is something that you have actually seen before. I am just going to be in this chapter forcing you to do this in a new way. Okay, I'm trying to give you as many tools as we can. When we get to the final, you'll get to just kind of pick whichever method works best for you, but you need to be familiar with all of them so you can actually pick the best one. All right? So for this particular problem I'm saying to find the sine and the cosine given that the tangent of theta equals 7 and given that the sine of theta is positive. Last chapter, I would have had you guys draw a triangle on this based on the fact that the tangent is opposite over adjacent, right? You would have done it geometrically. What I want you guys to do now is make use of your trigonometric identities, so your Pythagorean identities. All right. So let me ask you something really quickly. Don't write this down. Just watch. This is the common mistake, and I want to ask you why this is a common mistake. If I say that the sine of theta is equal to 7 and the cosine of theta is equal to 1, first of all, why am I saying that? Where do you think I'm even getting that? Shane?
Because tangent is sine of cosine, so 7 and 1 is equal to 7.
Yeah, so that's where I got that from. But what's wrong with that? Oops, I'm sorry. Oh, no, I am recording. Good. Why can't I do that? I'm sorry, what?
It's not in the range of sine.
It's not in the, yeah. 7 is outside of the range. Remember that the sine function, that graph is always trapped between 1 and -1, right? It is impossible to have 7 for the sine, which means that you've got something, it could be something rather than 7, maybe I have 0.007, and then the cosine would be 0. Right? Now is that in the range? It's in the range, but is that necessarily the fraction that the set that I have? That's just an example. Basically, all that it means to have sine over cosine means that whatever the sine and the cosine are, they're going to simplify to 7. You don't know what combination that is, though. So we can't use that quotient property quite yet. Instead, what you want to use, I'm going to erase that. Can anyone think of which identity maybe I could use with that tangent to figure out some other trig function? Would you be able to find, let me help you out, would you be able to find the secant? How could you find the secant? The Pythagorean identity, and once you know the secant, what comes easily from the secant? The cosine is the reciprocal. So I can use that. Let's take a look at that. So does anyone remember what is the identity that involves the tangent and the secant? How does that go? Tangent, just tangent? Square root of theta equals square root of theta. All right. I know that my tangent of theta is 7, which means I can plug in 7, and then I'm squaring that tangent value. Plus 1 equals the secant of theta, or secant squared of theta. 7 squared is 49, plus 1 is 50. All right. And so, what is the secant? Huh? Square root of 50, which is, yeah, 5 root 2 when you pull out your perfect square. And when I square root things, it could be plus or minus. I'm going to have to go back later and figure out whether it is plus or minus based on the quadrant information. So I'm going to deal with that in a little bit. If the secant is plus or minus 5 root 2, what are the possibilities for the cosine? Plus or minus still, right? One, yep, just the reciprocal. And I do not need you to rationalize, so you can leave that root 2 on the bottom. That's fine. Now that I know the cosine, how am I going to find possibilities for the sine? Yeah, you've got a couple of different options at this point, right? You could use the Pythagorean theorem with the sine squared plus the cosine squared equals 1 and plug in what you know for the cosine and solve for the sine. Or now you can use the quotient identity. You can use the tangent equals sine over cosine because now you have one of those sine or cosine numbers and you know what the other one would have to be to scale down to 7. Okay, which way do you guys want to do? Do you want to use the quotient or Pythagorean theorem? Just shout one out. It really doesn't matter. Okay, we'll do quotient since we've already done the Pythagorean theorem on this problem. I want to show you why it's okay to use the quotient now. So at this point, I can take this and find the sine by saying, well, I know that the tangent of theta is equal to the sine of theta over the cosine of theta. Now last time I just told you not to use this because we said, well, we don't know which combination of sine over cosine is going to simplify to 7. But now that you know one of the numbers, you're kind of forced into finding exactly what the cosine would have to be to simplify to 7 with that sine value, or cosine value. Okay, so sine is what I don't know. I now know that the cosine is plus or minus 1 all over 5 square root of 2. And so what I can do is get rid of all of this by doing what? Multiplying it up here. And so that will get rid of it down here. That means that the sine of theta is equal to plus or minus 7 is on top over 5 square root of 2. Does everyone understand why I can use the quotient on that second step but not the first step? Yeah? Okay. At this point, though, I need to make sure that I've got the correct signs on things. So what I'm going to do is go back up and see, kind of ask myself about my quadrants. So if my tangent value here, you'll see my tangent value is positive. What quadrants is it possible to have a positive tangent value? Quadrant 1 and quadrant 3, right? I am also told that the sign has to be positive. Where is the sign positive? 1 and 2, because the sign is my y value. So what's my overlap? Quadrant 1, right? So in quadrant 1, do I have any negatives ever? Yeah, so you would say in quadrant 1, there's no negatives. And so therefore, my final answers are going to be that the sine of theta is equal to just the positive 7 over 5 root 2. And my cosine of theta is equal to the positive 1 over 5 square root of 2. Make sure you check the quadrants at the end. This is the most forgotten part. In this case, you know, it ended up being both positives, but if something should be negative and you leave it off, you're going to lose points for that. Any questions on that? Okay. Next example. This is where we want to use some of the new properties I told you. So on the very first one, I want you to find the cosine of negative theta. Now this would be easy using the odd-even identities I gave you guys if you knew what the cosine of regular theta was, right? Based on the fact that I told you that the sine of theta is 5 over 8, can you find the cosine algebraically without a drawing? Which identity would you use with the sine to find the cosine? Just like the last problem, what did we use to start? Yeah, so we're going to use the Pythagorean theorem. We just identified that we need to use the sine squared. Oops, I don't want that color, sorry. The sine squared of theta plus the cosine squared of theta equals 1. We're going to plug into that and find the cosine of theta. So the sine is going to be 5/8 squared plus the cosine squared of theta equals 1. 5/8 squared is 25/64 plus the cosine squared of theta equals 1. So when I subtract my 25/64 from a full 1, how many 64ths are left? 39. Good. So I'll have cosine squared of theta equals 39. And I forgot to give you guys information on this, so I'll hit that on the next step. Let's say, and let me just put it in right now before I forget. I want you to assume that you are in quadrant 2. All right, so knowing that, on this next step, take the square root. You have that the cosine of theta, if you take the square root, oops, I'm sorry, this should be 39 over 64, shouldn't it? Did I erase more than I wanted to? A little bit. So 39 over 64. When I take the square root, am I going to take the plus and the minus? Or since I've already told you I'm in quadrant 2, you're just going to take, for the cosine in quadrant 2, the minus. Yep, the cosine in quadrant 2 is a negative. So you'll take the minus square root of 39 over 8. Whoa, sorry, that's really super small. Can you guys read that decently enough? If not, here, let me try this. Square root of 39 over 8. There, that's better. All right, so I now know what the cosine of theta is. If the cosine of regular theta is, well, here, let me go back. Based on your odd-even identities, what is the cosine of negative theta in terms of just the cosine of theta? Is it a plus or minus of the same thing? Based on your odd-even. It's equal to the regular cosine. Remember, the cosine is an even function. So that means that the cosine of the negative theta, which is what I'm ultimately looking for, that is the same exact thing as what I just found. So this is still the negative square root of 39 over 8. Are there any questions on that? Yes.
Can you just use the cofunction identities like pi over 2 minus all these?
For the first one?
Yeah, and then do the other.
Not really, because then you're going to have a pi over 2 and you don't know what the sine of pi over 2 is. Like, so in other words, if you tried to use the cofunction, your next step would be to say that the cosine of negative theta is equal to the cosine of theta, right? And then you would have to say, if you wanted to use cofunction, that would be saying that that equals the sine of pi over 2 over pi over 2 minus theta. But you don't know what the sine of pi over 2 minus theta is. You know what the sine of theta is, and that's it. Do you see what I'm saying?
If that's on the calculator portion, can you do that specifically?
Do what?
The second one.
You don't know what theta is. Oh, I see what you're saying. To plug in, this is not going to be on a calculator portion. If it was a calculator portion, sure, but it's not going to be. Shane.
So is the cosine of negative theta equals cosine of theta, is that something that we're just going to have to memorize? Or?
Yeah, that's one of the identities I just gave you. Whoopsie. Yeah, that's the odd-even identities.
Yeah.
So yes, you do need to know for any of the 6 functions, if I ask you to plug in a negative theta, you need to know which ones have the negative result and which ones have just the regular result. Just the cosine and the secant, those are the only 2 that should not have a negative attached out front then. Okay? Do you see what I'm looking at? Okay. All right, so for part B, now we can use the cofunction identities. All right. The only problem is with the cofunction identities, what's different about this particular setup? And I know I've got it kind of squished in. We're looking at this now. What's different about this setup than the way I phrased the cofunction identities for you guys? Yeah? The theta and the pi over 2 are switched, and that does have a difference sometimes. So you just need to check it. What I would like for this thing to look like is I would like for it to look like pi over 2 minus theta, right? That's what I want, but that's not what it is. How can I force it? I can throw a negative out front here. So I can switch the order if I pull out a negative. Are there any questions on why that is? Okay, now the problem is that in order to use the cofunction identity, I don't want that negative there, but you can use your odd-even identities with the cosecant. With the cosecant, when you have a negative in the input and you want to take it out, what do you have to do? So in other words, kind of a side note, cosecant of negative theta equals what? Negative cosecant of theta or just regular cosecant of theta? It's the negative cosecant of theta, right? So what I can do, all that this is saying is that you can take the negative away from the inside if you tack it on out front for a cosecant. Whereas in the cosine, we didn't take it out front, right? All right, so I'm going to backtrack on that, but my next step is going to be to take that negative out so that now this does look like one of my cofunction identities now. I have the pi over 2 minus theta in the correct order. Okay, so for this part of it, just for this part right here, I can replace that stuff. What's the cofunction for cosecant? Right, so I can replace all of that stuff with the secant of theta, just regular old theta, but I do need to carry that negative that I've pulled out down. Okay, now the secant is just the reciprocal of the sine, right? Or I'm sorry, the secant is just the reciprocal of the cosine. So this secant stuff is actually just going to be what we found for a cosine, which our cosine was the reciprocal of it, is negative 8 over the square root of 39. So that's just taking this cosine stuff right here, switching the fraction, that gives me the red secant stuff. But again, we still have this negative sign that we're pulling down. So this actually ends up being positive 8 over the square root of 39. Signs are going to matter. That's going to tell me whether or not you really understood the sequence of the steps. Okay? Are there any questions on that? Okay. So as I'm sure you guys are noticing, these are basically just giant puzzles. I'm giving you the tools. Something that I'll kind of give you a heads up on right now. Hold on one second, guys. I need to get my computer back up. Okay, guys, something that I did want to kind of point out that I was just about to try and say. These are just giant puzzles. This is not like algebra. Shh. This is not like algebra where you can just kind of memorize a sequence of steps, okay? All I can really do is give you all of the identities, but every single problem is going to go differently. I can't teach you how every single problem goes. I'm going to show you some of the tricks that you're looking for, but you guys are going to have that list of identities in front of you, and you're going to have to figure out how they fit into that particular problem. It is going to be different every single time, okay? I'm going to give you a heads up that most of you guys, when you do your homework, are going to go down the wrong direction at first, so you're going to try the wrong thing first and get kind of stuck, and that's fine, and you need to be ready for that. You can't get to try 5 steps and be like, oh, I got nowhere with this, so I'm just going to throw it down and walk away. Okay? No. All you have to do is erase your steps or cross them out or whatever you're doing and just try something new. With these problems, it really is a matter of if you're getting stuck, erase it, start fresh. Okay? And it's going to happen to you, and just be ready for it. Okay, so here's kind of where things start to get a little bit more intricate. I'm going to be giving you these expressions, and you need to simplify them down to either a single trig function or a number. Okay? Using the identities that I've given you. Here's the puzzle, is that you need to figure out how these identities are interwoven in here. A lot of times, kind of my biggest hint to you is that a lot of times, not always, you want to do anything that's suggested algebraically. So any factoring, if there's distributing, if you have fractions, combine them, things like that, okay? Here, do you see some sort of factoring that would be possible? Okay, you cannot do that. And let me show you why. No, this is, the other class said it, and it's a perfect example. If I wrote f of x, would it make any sense for you to be like, that's xf if I take the x out? Does that make sense to you? No. And you guys, the sine of x, sine is a function. So for you to be like, I'll just take the sine out, then what do you have for your input? Nothing, and that's bad. Okay? Do we all understand why we can't take an x out? Okay. So that's bad. What can you take out, though? Cosecant. I can pull out one cosecant out of both of those terms, right? If I pull a cosecant out of this very first term here, how many are left? 2. You took one out. So you have 2 cosecants left. I took the cosecant out of this second term, so that's gone. What's left? This is gone, right? I took it out. So just minus 1, no, minus the cotangent squared of x. That's what's left over off that term, right? This piece right here should be raising a red flag. What does it potentially look like could be happening? Could be a form of one of the Pythagorean identities because you've got these squared pieces, right? And you've got the cosecant and the cotangent together. That's a pair that's together in one of the Pythagorean identities, right? I'm going to write it off to the side so that you guys can kind of look at it and let me know if you see it. So what I would recommend is having the Pythagorean identities next to you. If you do, you would at this point have 1 plus cotangent squared of x equals the cosecant squared. That's one of the identities that you guys found, or that you know. So does this somehow morph into this piece over here, is my question. How? So yeah, all we did was we would have subtracted the cotangent over, right? If you recognize that, what can I replace this whole thing with? 1. And now, what happens? So if that whole thing is 1, and this cosecant is still hanging out here, what does this whole thing equal? So you got it down to one single trig function, which is your goal. Yes, Shane?
So when you took out the cosecant of x, don't you have to divide cotangent by cosecant of x and then it be
No, because I took out, so here's my original term, right?
okay. Oh.
I took this out, so that was the division on that whole term. That got rid of that term. This is what was left. Do you see that? That's where it went. Okay, are there any questions on that one? So a lot of times you want to start these problems by looking at, can I take a common thing out of all of the terms? If you can, that will typically help you. So that would be one of the first things to check. Let's try another one. All right. This should have some red flags for you. What are you seeing right away? What? Spots? What do those individual numerators and denominators look like they could be coming from? They look like they could be coming from the Pythagorean theorem again, don't they? So this top one looks like maybe it came from which Pythagorean theorem? Yeah, it looks like it maybe came from this guy, right? So let's see if we can figure out how we would get it. How would I have gotten sine squared of theta minus 1 from this piece? And you want to be able to do this visually and not have to write it out every time, so I'm going to talk you through it visually. How did I morph this guy to get this? What did you do? Yeah, you would have taken the cosine over as a negative and subtracted the 1, right? So what does this whole thing equal then? Yep, that equals negative cosine squared of x. That negative is important. That sign would be a very easy thing to forget about. Okay, let's take a look at the other piece. Where does it look like this guy potentially came from? What's the original identity? Yep. 1 plus the cotangent squared of theta equals, cotangent goes with cosecant. Okay, so how did I morph this piece to look like this piece? What did I do? Did the kind of the same thing. Subtract the cosecant over, subtract the cotangent over, so that piece actually equals positive or negative cotangent? Negative cotangent, very good. So this actually ends up being a positive. And it still isn't done though, because remember I need this to either be a value or a single trigonometric function. This is not a single trigonometric function yet. So these are going to become positives, but now what do I have to do to get that even further? Yep?
Can you because you know that cotangent is cosine over sine.
Yep. So my next step might be to recognize that in the denominator here, the cotangent is the cosine squared of theta over the sine squared of theta. I'm going to caution you not to simplify it, knock out the cosines there, because then it might look like it's 1 over the sine, and it's not. Think about how would I take this whole thing and move it up here? I'd multiply by the reciprocal is the same thing as dividing by a fraction, right? So I can take that off the bottom by multiplying it, and then you'll see where does the sign actually end up? On the top. And it would be easy to think that it's on the bottom on that previous step before doing that work. So I would definitely take the time to flip fractions up to see where things are actually canceling to. Are there any questions on that one? So that would be considered final because it's down to one trigonometric function, right? It can be a power of that function or a multiple of that function, but it just can't have another trig function with it. Okay. I don't know if I can, to be honest. I'll try. I don't think I can. I'm sorry. Can you look at your neighbor? Okay. I'll give you guys a second to catch up. Okay. We've got one more of these, and then we're moving on to the next concept. Again, you kind of want to do what is algebraically being inferred to you. So naturally, like where does your natural instinct, what does it want to do when you see two separate fractions? Run as fast as I can. No, what is it? What do you want to do? You want to combine them. How do you combine two fractions? Find a common denominator. Okay? So in this case, it's going to be to your benefit to combine them with a common denominator. What is that common denominator going to be? The multiplication of those two things, right? They don't have any common factors between them, so you're just going to have to force it to be combining those. So on this fraction, what would I have to multiply the sign of x by to pick up the common denominator here? What do I have to multiply by? I need to multiply by the sine of x. So that's going to become sine squared of x to force the common denominator on that piece. Over here, what am I going to have to multiply this by to pick up the common denominator? Yep, the same thing, 1 minus cosine of x. So that's going to look like 1 minus the cosine of x quantity squared. Now what does your natural algebra instincts tell you to do? Huh? Multiply. FOIL, yeah, you want to FOIL this out, okay? So some of you might benefit from writing that all out. and saying, okay, well, squaring it means the same thing as multiplying it by itself, right? And so what does that look like? We still have our sine squared of x. That is still going on. Plus, when I FOIL this out, you've got your first times your first, which is 1. Your outer, which is going to be a negative cosine of x. And your inner, which is going to be another negative cosine of x, will become minus 2 cosine of x. And then your last is going to be plus, because of the two negatives, plus cosine squared of x. Are there any questions on that part? All right, take a look at it. It's a puzzle, remember. What can you guys see that you can simplify? What pieces can you combine together to simplify? Raise your hand if you think you've got it, so I can have one answer. Ian? Yes. Because sine squared plus cosine squared equals 1. So we can simplify that down to 1. Those two pieces will go away, and I now have 1 plus 1 minus 2 cosine of x over sine of x times 1 minus the cosine of x. Keep on and you guys, you just kind of want to go with where your natural algebra instinct takes you, like I said. If it doesn't take you good places, just erase it and try something new. All right? But where do your instincts want to take you now? Add the 1 plus the 1. Very good. So that's not too difficult. That's going to become 2 minus 2 cosine of x all over sine of x times 1 minus the cosine of x. Now where do your natural algebra instincts take you? I'm sorry, what? Add the 2. Factor the 2, I'm sorry. Yes, factor the 2 out. I heard add 2 and I was like, what? And now what do you see? Those go away. Right? You get two pieces that cancel. This is 2 over the sine of x. What might be a neater way to write that? A more condensed way to write that same thing. 2 cosecant of x. I can get rid of the fraction that way, right? Either of these would technically fit the bill because I just say simplify it down to a single trig function. So technically 2 over the sine of x is a single trig function. It's just that 2 cosecant of x is a little nicer looking. So that one got a little bit more difficult. But again, just kind of, one step at a time, what looks good to you. Any questions on that one? Yes. It's the same as the quantity of sine x squared, but it's not the same as sine quantity x squared.
Okay, so you can't do this like if it was like x squared.
Right.
Okay.
Okay. Next problem. So I just tried to give you guys a few different examples on simplifying because, like I said, all of the problems are different. That's going to be the same sort of thing with these solving trigonometric equations. All of them are going to be a little bit different. Okay? Notice that this is a different problem because I now have an equal sign and I'm actually asking you to find solutions. So I'm asking you to solve this all the way down for x's that you could plug into the angles and get these two sides equal. That's what your goal is now. Specifically, I want these in between 0 and I want any possible solution that you could plug in between 0 and 2 pi. Okay? Now, I'm going to do something really quickly and I want you to tell me why this is just a terrible, terrible, terrible thing to do. Oops, I'm sorry, I accidentally skipped a slide. Go back. My bad. Am I still on the wrong slide? I'm sorry. Got it.
Yes.
Why is this? Oh my gosh, I am going to have a heart attack. Why does this? Okay. I am ready now. Why is this a bad move? Well, sadly for you, you'd be missing out on some solutions then. Why is that bad? Is it what? No, that's fine. What can you never ever divide by? Is it possible for the tangent of x to equal 0? It is possible. And so therefore you can't divide by it because you could potentially be dividing by 0 in that sense. Okay? So you never want to divide by anything with a variable that could be 0. Okay? That would be bad news. So we don't do that. What do I do instead? Like, let me help you out here. If this were 2x squared minus or equals x, what would you do? You wouldn't divide by x because x could be 0. Instead, you would... No, you would not. Get it in quadratic form? In which case you would subtract over the x and get it equal to 0.
Got it.
All right. Ready? What do I do? Subtract the tangent over. I cannot divide it, but I can subtract. Now what do you see? Based on what I was talking about on earlier examples. Natural algebra things to look for. Factor out. Any questions on that? No? Okay. When you get two factors equal to 0, what can you do with them? Set them each separately equal to 0. It's like magic.
I'm pretty sure it is.
Except for this magic is just pure logic. That's all you need. Okay. Notice that, you guys, here what I'm asking for is what x values, which angles in between 0 and 2 pi on the unit circle would give you a tangent value of 0. Remember that the tangent is sine over cosine. In the unit circle, sine is the y value over the x value. So when in the unit circle would you get a y value that's a 0 so that you get 0 over a number to equal 0? When is the y value 0? At 0 and pi, and technically, since we included 2 pi, right? It's the same thing as 0, so it doesn't really matter. But those are the three angles where you would get the tangent of 0 equal to, or the tangent of those angles would be equal to 0. Now I need to solve the other piece. And what did I forget to put in there? X. Sorry about that. Drop my variable. So for this one, you just want to get your trig function by itself. So if I did that, I would have sine squared of x equals 1/2. So what does the sine of x equal? Yep. Plus or minus the square root of 1/2. Now, if I'm not giving this to you on a calculator, if I'm giving this to you on a non-calculator portion, this is going to resemble one of the pieces that you should know in a trig function. What does that simplify to? And let me help you. I'll give you a hint. This is the same thing as this, right? Which is, yeah, that is root 2 over 2 if you rationalize it. So you have to be able to morph that down to see that it actually is one of your pieces that you know. So where on the unit circle, would a sine value equal plus or a minus square root of 2 over 2? Which angles? Pi over 4. I want all angles between 0 to 2 pi. Negative pi over 4 does not fall in between 0 to 2 pi. So you need to go around counterclockwise. And 5 and 7. Very good. Okay. So your full set of solutions, when you list these, when you give me your final answer, you want to list them in order. So in order, this would be 0, pi over 4, 3 pi over 4, pi, 5 pi over 4, 7 pi over 4, 2 pi. I don't really care if you have that 2 pi on the end, and it got stuck in the dosiri thing. I don't care if you have the 2 pi in the end as long as you have the 0. One or the other is fine. You don't have to really duplicate the 0 and the 2 pi. That's okay. Are there any questions on how we solved this equation? What? Don't want to repeat that? All right. All right, find all solutions without a calculator. Yeah, guys, for these, I mean, really all I can do is just give you as many examples as I can because, like I said, all of the problems look different. So I'm just trying to show you as much as I can in the time I have. I know it's tedious. No, so this problem is just saying find all solutions, and that's something to watch out for, and we'll talk about that. All right, so guys, this one says to find all solutions in general, so not just in between 0 and 2 pi. Now, if you want to find these solutions, your first goal should be, you want to first see, if you have more than one trig function, can you take one of the trig functions out like we did in the last one and get two different groups with single trig functions? Can you do that here? No. Which means that I need to somehow convert this so that it's all in terms of sine or all in terms of cosine. Which one of these terms can I switch using one of our identities? Which one of these terms can I modify? Can you modify that? Can you write that in terms of sine somehow? Maybe. Yes. Yeah? Yeah. Why I have to? Because you need to get down to, so the question was, why do I have to eliminate one of the trig functions? The reason why is because I need something like on the last side where I get it down to a single trig function equal to a value, and then I can look in the unit circle for that. There's no way that you can have something like if I asked you, oh, when does the secant x times the sine x equal 3? That's going to get confusing, right? So you really want it to be in terms of 1 per factoring. Now, if I can't pull something out, then I'm forced to write it all in terms of the sine so I can factor it all in terms of the sine.
So the reason why it was okay on the last one was the whole thing out.
Yes, so you got one group was in terms of tangent, but the whole other group was in terms of sine. So separate factors were in terms of separate things. That's okay. Okay, so on this one, I am switching the cosine squared of x to be 1 minus the sine squared of x. Where did I get that? The Pythagorean identity. Yep, very good. So what happens here is I get 3 sine of x plus 3 minus 2 plus 2 sine squared of x equals 0. And now I'm going to put that in quadratic form because it looks quadratic. So I can write this as 2 sine squared of x plus 3 sine of x, and then I can combine my 3 minus 2 to be plus 1. What are you thinking here? Why did I put it in that form? Because now I can factor it. All right, so factoring this, I need my very first terms to multiply to 2 sine squared. So that means one of them has to be 2 sine of x. One of them has to be just regular sine of x, so that it multiplies to 2 sine squared of x. It's basically like regular old factoring, except for instead of just using x for your variables, you're using sine of x. What do my last two numbers have to be? 1 and 1 to multiply to 1. What are my sines to add to 3? Plus and plus, right? So I would set each of these factors equal to 0. This factor, the very first factor, if I set it equal to 0 and solved it, I would get the sine of x equals negative 1/2, right? Which x values, so first you want to identify which x values in the unit circle give you a negative 1/2. So where is it possible for me to get a negative 1/2? For the sine. Remember, sine is your y value. I've heard it pi over 6 or 30 degrees. But I need all solutions, so technically any revolution of that is going to give me the same value out, right? So since I didn't specify for the 0 to 2 pi this time and I asked for all solutions, I need to add a 2 pi revolution times any multiple k. Yes? Oh, yes, I'm sorry. Thank you. I missed that. 5 pi over 6. Thank you. Yeah. And then which other quadrant could I be in? That was in quadrant 2, and I could also be in quadrant with a negative sign. Quadrant 4. And what would that be? 7 pi over 6. Negative 5 pi over 6? Yeah, you could do that.
No, negative pi over 6.
Oh, no. Sorry, quadrant 3. I'm sorry, I meant to say quadrant 3. I was thinking quadrant 3. The sine value is your x value, which is negative in quadrants 2 and 3, right? So you need to go back. You need to go back and look at your unit circle if you're not following that.
So is the sine y going? Yeah, is the sine y?
Oh, yes, it is. But either way, that still is in quadrant. Okay, hold on. Yes, I am being all sorts of mixed up right now.
I'm a little bit more confused.
I'm sorry. So let me erase those. Starting over. Sorry about that. So, guys, I only have a few minutes. I need you to just hang with me. All right. Yes, thank you for catching that. The sine value is the y value. Okay? So the y value is negative in quadrants 3 or quadrants 4. So in quadrants 3, that would be 7 pi over 6. In quadrant 4, that would be 11 pi over 6. And yes, you could write that as negative pi over 6. As long as you add on your full revolutions because of the way that I've worded the problem. I want all solutions. And adding that 2 pi k allows that. For the other piece, you have the sine of x equals negative 1. Where is the sine of x equal to negative 1 in the unit circle? Negative 1. 3 pi over 2. And then add on your full revolutions times k. So these are all down here, your possible solutions. Sorry about the mix-up on the sign. That would be my bad. Good catch. Okay, I'm going to move along. I only have a few more minutes, so I'm going to try and finish this out. I think I only have one more example. Okay. All right, for this last example, this is actually a pretty straightforward one. The directions in the book are the same exact as this. So it says make the suggested trig substitution. What they mean by that is substitute this trig function in for this x, and then see how you can use Pythagorean theorem identities that we learned to simplify it down to a basic trig function. Okay, so if I do that, I get the square root of 36 minus, and I'm plugging in 6 sine squared of theta, or I'm sorry, 6 sine of theta squared. So I need to, in that group, square both the 6 and the sine. So that will be 36 minus 36 sine squared of theta. What you are not going to do is this. Why are you not going to do that? Because Mrs. Stevens will put you in prison. In math jail. Okay? All right. Do we all see why she'll put you there? Remember, you can't break a square root by addition or subtraction. You can only break it by multiplication or division. So this is bad. All right? So we won't do that. What can I do at this step instead, though? Factor the 36 out of both terms so that I do get multiplication. That'll be nice. And then it said to use Pythagorean identities. Where do you see the Pythagorean identity playing in here? What does that become? What is 1 minus the sine squared? What? Okay, there we go. Cosine squared of theta. Now you have multiplication, so you can break this down. Okay, now why is it not good for me to leave it at this? Let's see if you guys can find it. Well, I didn't actually physically take the square root of two sides, right? I was given a positive square root, and that's it. So I have to keep the positive square root. Is it possible for me to get a negative value out of that cosine? Yes. And would that negative value equal my original thing? Really? Is it possible for this to ever, ever, ever be negative? So should it be possible for this to ever be negative? How do I remedy that? Dunzo. Yep. All right, there is your homework. It will be due on Friday, and it's posted on Schoology, along with this lesson. This lesson is also going to be posted on Schoology.